Craig. I work for Dendra Systems. And I'm going to be talking today about how we've used Terraform and AWS Batch to help us improve how we handle processing of large data sets. So who are Dendra Systems? Dendra Systems are an ecosystem restoration services company. We combine ecology and data science, machine learning, and drone automation to produce a number of services that we provide to help customers restore ecosystems. So the sort of services we offer are things like weed identification and monitoring analysis, erosion monitoring, carbon quantification, and seeding as well. So what you're seeing on the screen is one of our seeding drones that we use to help people spread seed and restore areas. What I'm going to be talking about today is on our imaging side. So the drones we fly can capture ultra high resolution images that we can use to help us identify weeds and other things. And obviously that involves processing a lot of data. Up until recently, we've been doing that processing in offices local to where the data is being captured. But as our company's grown and our scale's grown, we're doing more operations, and that's becoming increasingly untenable, not cost effective anymore. And we've heard that all the cool kids, they do their processing in the cloud. So we thought, we'd give that a go. And that's what I'm going to be talking about today. So the first part of the problem is data ingestion. How do we get all of these multi-terabytes of drone imagery up to somewhere we can actually work on them? And this bit's quite simple, really. We're recording these images onto hard drives, and those then get shipped to a colo. And that colo has a AWS Direct Connect connection on it that gives us nice, stable, and reliable uploads up to S3. And we can scale that up to between 5 and 10 gigabits per second, depending on the particular colo and what connection they have available to us. So that solves that sort of bit of the problem quite nicely. We can get our terabytes of data up into the cloud. Once it's there, we actually have to do something with it. And what does that look like? Well, so as our drones are flying, they're capturing individual, what are effectively raw images, if you're familiar with digital photography. That tens of thousands of those over a particular flight. And we need to take those raw images and both convert them into formats that additional software can be used to process them, or to do additional processing rather. And we also need to apply some color corrections at this stage. So that gets us a more homogeneous set of these individual images. And then the next phase in the processing is to take all of these individual images and take the camera calibrations and various bits of data that we can get from the images and stitch them all together into what's called an orthomosaic. So this is an extremely large single raster image that represents the high resolution imagery over an area. So this is taking, say, a terabyte of data and turning it into half a terabyte single raster file. Once we've got that single raster file, that's not particularly usable or digestible. So we then have the final step in the process that I'm going to be describing today is then slicing that up into tens or hundreds of thousands of individual tiles. These are the same sort of tiles you'd be used to using in Slippy maps, like Leaflet and things like that. So we can use this as a layer that our customers can use to analyze what we've captured. But we can also use these tiles as inputs to our machine learning services that can then look at each tile and identify individual weeds within those. So that's the pipeline that I'm going to be discussing today. As you might imagine, each different step in this pipeline requires quite different resource requirements. For example, conversion is very CPU intensive, stitching is very, so orthomosaicing is very GPU intensive, so we have multiple GPUs required for that. And then the slicing into individual tiles can be quite memory intensive. So each different step has different resource requirements. And in an ideal cloudy world, we would spread this across multiple different instances, each of them that are appropriate to those workloads. And you'll also see quite immediately that we have quite different scaling characteristics across the pipeline. Some of it can be massively parallel, and then we're reducing down to actually quite a narrow bottleneck in our pipeline. And that's both because we want to stitch reasonably large areas to get effective orthomosaicing, but also that orthomosaicing is quite constrained by the number of licenses we have available in a pool to do that work. And yeah, we can only afford so many of those. So we have that constraint as well. So as I said previously, this work has previously been done in our offices. And my job in this first version of our pipeline was to take it onto the cloud. So we approached this problem by trying to take a sort of incremental approach to it, and by starting off by using the existing Python scripts that we'd already written over multiple years to process the jobs locally, along with some additional ones we added. These were refactored to accept S3 and in and out URLs. We wrapped each of these scripts individually in Docker images. And then we used Terraform to set up AWS Batch. So an AWS Batch is, unsurprisingly, a service from AWS. It's essentially a wrapper around ECS, for those familiar with that, a container service. And it provides quite a high-level way of essentially running command line scripts on the cloud. So you give it a Docker image, and you give it the command that you want to run as the like you would run Docker run, so the appended to the entry point of the image, and it just runs it. It sets up the EC2 instances for you, it scales them if it needs to, it packs them as it needs to, and yeah, it was quite a nice incremental stepping stone in our journey to processing online on the cloud. So, and then, we had a simple Python script to wrap the upload process and kick off AWS jobs as we needed them. So I'm going to be just concentrating on our Terraform setup here. And I want to prefix this by saying I'm not a Terraform expert. This was my first Terraform project. And one of the reasons I thought it might be useful to present this is just quite a simple incremental run through of how I went about producing our system with Terraform, and sort of stepping through the process I went through that in quite a simple way. So yeah, this was from scratch in Terraform, so we weren't importing any existing infrastructure into our configuration. It was just, I literally started with an empty Terraform file and went stepped through the configuration, creating it as I went. It's just a simple main Terraform and a variables Terraform file, none of these fancy 0.13 modules or anything. It's only about 300 lines of config. I'll go through most of that today, although I'll be skipping over bits of it, you'll be glad to hear. Yeah, so what does that actually look like? So hopefully you can read these, hopefully they're big enough. So start off by, similarly to how you saw in Marco's talk, we define the provider that we're using, and we're just pulling in some variables from our variables file to define the region and the allowed account IDs. We're not doing anything clever like we probably should be to do with like having multiple AWS accounts here. So yeah, just a really simple provider config. We then configure Terraform. Again, this is pretty boilerplate, I think, in terms of just setting up where we're storing our Terraform state and how we're going to handle locking that state file. Again, I think that's pretty much standard here. Now we actually get into starting to create things with Terraform. So the first part of getting a working AWS Batch pipeline going is you need somewhere to store your Docker images. So here we're using ECR repository. This is just a container repository where you can upload your Docker images with Docker push. So we create that. Now we're going to do our Docker building and pushing outside of Terraform. So we need to know where we want to push our images. So we describe an output, and that's just the repository URL. And we can point the value of that to, I can use my mouse to point that, the value to the ECR repository pipeline repository URL. So if we ran Terraform apply now, it would create the repository for us and then give us that URL as a nice, prettily printed output. Great. The next part is probably one of the more complicated bits in terms of setting up AWS Batch, at least as far as I'm concerned, because I find AWS's role definitions, IAM role definitions, completely baffling and baroque. But the first part of this is to describe your IAM policy document that defines with your assume role policy, and then associate that with an IAM role resource. Now, you could actually inline this, but I found it a bit easier to read by separating this out with a data block. It just makes it a little bit easier to digest as far as I'm concerned. That done, we can then set up a separate policy document to actually describe the policies that if you need additional access to other other AWS services such as S3 or CloudWatch, or anything else that you might need as part of your actual job. And then we set up an IAM role policy resource to associate that with the role that we've just created. That's quite straightforward. Then, for whatever reason, because this seems the way IAM seems to handle this, is just to continually attach policies to things. And if I'm cargo culting this and this isn't how I should be doing it, then please do tell me. So yeah, this is defining a role policy attachment that's just setting an existing policy to be attached to our existing role. And then probably the most baffling thing for me is when we take this role that we've created and we wrap it further inside an IAM instance profile. And it's this IAM instance profile that will actually attach to EC2 resources or EC2 instances in our definitions as we go forward. So that's our IAM role setup. I should have clarified, this is describing setting up the IAM role that we're going to attach to EC2 instances. You would also go through the same process or a similar process for setting up a second IAM role that is used by AWS Batch itself to run its commands. That's very similar to this, so I'm going to skip that. So we've created our IAM role. We now need to create a security group, and this is what our EC2 instances are going to be created within. And this is just a really simple example of an open egress security group. We then need to define what's called the AWS launch template. So this is actually optional in Batch, and it's what Batch will use to instantiate, when instantiating our EC2 instances. It's a way of providing configuration there. The reason, and essentially what I'm doing is using it to hard code the host image that we're using when we're setting up the EC2 instances. And this is part of the nuances that cause some confusion with Batch, is that it will change which Amazon Linux version it defaults to as the host image, depending on which resources you request. So if, for example, you request GPUs, it will change to Amazon Linux 2, whereas normally it will default to Amazon Linux 1. And this will change things like the block structure that the host is set up with, and that can cause some pulling of hair when you're trying to figure out what's going on there. So here we're just hard coding the host image ID. So with that all done, we can actually start creating our batch config itself. And this is where we start to pull together the different bits that we've been creating. So here you can see that I'm defining the instance role that I talked about creating before. We're deciding what instance types we want Batch to be allowed to create. We can set some scaling rules, so things like the maximum vCPUs it can use, so it can't scale instances beyond this limit. And you can set how many instances to have in a reserve effectively by having your min CPUs set. We describe the security group. Here I'm using a subnet just coming from a variable. This is something I could never really get to the bottom of, or haven't got to the bottom of yet, which is that occasionally if I try to do automatic subnet detection, I'd get allocated to a subgroup that didn't have the instance types that I needed. And that might be something I need to look into further in terms of maybe querying to get subnets that have particular instance types. We then specify the launch template we're using. Here we're passing in the service role that I talked about. And then we get into some meta, I think they're called meta attributes or meta parameters in Terraform that aren't part of the batch config themselves, but are telling Terraform how to handle this resource. So we're saying that it should create before it destroys. So it should create a new compute environment before it destroys the old one. This is to do with external dependency issues. So there's a dependency between job queues and compute environment that Terraform doesn't handle tremendously well, and you have to sort of guard against that. And there's a similar thing with the role policy attachment that requires an explicit dependency for. Yeah, I think that's all I need to say about that one. We then describe the job queue. So these are just really simple queue primitives. We're setting the compute environment that this queue is going to feed into and what priority we want to run it in. The particular queue structure you choose will obviously depend on what your pipeline actually looks like. We just went with a simple having queues for each step. There's nothing much more to that. You then have a separate job definition description. Here, so these are for our auto-mosaicing job or stitching. And this is where we describe the image that we want to point to. And you can see we're using the URL for the ECR repository that we created at the start and just giving it whatever hard coding in the tag here, which is, and then we're describing the command that we want to run by default. So this is what will be appended to the entry point of your Docker image. We can describe the resources that this job needs to run. So how many vCPU shares, what memory it requires. Here we're just saying that this job needs 2 GPUs to run. Yeah, and then Batch will use that information to either spawn new instances or pack these jobs into existing instances. So yeah, that's all we need to get AWS Batch working. But how do we actually make it go now? So like you saw Marco using, you run Terraform apply and it will spit out a long plan of what resources it's going to create or change as part of this run. And then with this config, you'll get the nice repository URL output. We can then tag our Docker image with that, push to that URL, and after waiting a while for that to finish, you can then just, if you want to, do nothing more than run from your own command line AWS batch submit job, give it a name, define the queue that you want to run against, the definition you want to run against, and it will spawn that EC2 instance for you and run the your command line. Obviously, you can pass in additional parameters here to customize bits of the job definition. But in reality, what you'll end up doing is using whatever SDK you prefer, like Boto3 for Python, to create a script to help you do this. I should have mentioned, actually, going back to the job definition, there is limited support for parameterization here, so you can create a sort of interface if you like. It's quite limited in terms of what you can do in terms of things like default values. So we ended up just overriding the command container property every time that we ran a new job definition, or submitted a new job, I should say. So that's where I'm going to sort of leave talking about the config stuff. Hopefully that wasn't too hard to follow or too dry. In terms of lessons that I took, whether they're useful to anybody else. It was really quick and easy for us to get something up and running with Terraform and Batch. I found the Terraform documentation extremely approachable and really good, and far better than the AWS documentation in most cases. So it's actually easier to learn AWS Batch through Terraform than learning it directly. The AWS launch template is not well supported in Terraform. There are issues there, sort of open bugs that have been around for a couple of years now to do with support for things like changing EBS block types and CPU options. And there's a few different changes that won't get detected properly for you. Like I discussed briefly, there are the sort of things that will make you pull your hair out with Terraform with an AWS batch, or things like the external dependencies between the job queues and the job definition, so the compute environment and the job queues. It caused a lot of sort of confusion and delay for us to figure out what was going on there. And essentially, I ended up cargo culting my way to try to get it fixed. I'm not sure whether the fix is even the right one or which bits I need, but it works now. In terms of batch, it's a pretty limited service. It's pretty high level and doesn't really help you very much in terms of things like monitoring the status of your jobs, and debugging can be pretty poor. And because it's layered on top of additional AWS services, issues down in the things like the EC2 or C layer or the ECS layer can be masked from you in terms of the outputs batch will give you. So that can be quite frustrating. Because it has this interface in terms of it's designed around command line options and essentially success or fail statuses, you're pretty limited and you reach these limits quite quickly, I found. And the other limit we ran into is it has a concept of dependent jobs. So you can define when you're submitting a job that this job is dependent on some previous job ID. And that's limited to a 20 job limit. So when we had tens of thousands of images that we needed to convert, we had to track the status of those jobs outside of batch and then create the dependent jobs, well, semi-manually ourselves, essentially. And I think that's it for me.